So in this video, now we're going to measure voltage and current through a parallel circuit, which all that means is just that now electricity has more than one option to flow. So what that means is here's the positive terminal, electricity flows through the red wire. Before it even encounters this bulb, it can either choose to go into the bulb or go through this wire. So the current splits at this point because some electrons are going to be like, I want to go through here, or not electrons, some current's going to be like, I want to go through here, some current's going to be like, oh no, I want to go through this one, right? How much current, we're going to measure it, but for right now, I want to measure the voltage. But it's important to note that the voltage in parallel circuits, as we just learned, remember, voltage doesn't change. Voltage remains the same across all branches that branch out of a pathway in a parallel circuit. So if I were to measure the total voltage, let's re-measure the total voltage of this battery pack. Remember, of using a voltmeter, I can just touch the probe circuit because you can connect them in parallel. So I get 2.53 volts. I'm going to count. 2.53 volts is the total voltage going into the circuit. Okay. Now let's measure the voltage drop across the first resistor, or the first light bulb, I should say. Remember, I could just touch it. Oh, hold on. And I get about 2.456 volts, which is good. V1 equals 2.5 volts around, and that better be around the same number for the second bulb as well. So higher potential red, lower potential black, and I get the same thing. Oh, you guys can't even see it, sorry. Same thing again. 2.43, 2.5, whatever. And that excess voltage, remember, escapes in the form of light and heat. So we just verified Kirchhoff's voltage law that says that voltage is the same through every branch in a circuit. Okay, but the voltage between this point and that point better be zero. And I can also measure that. Let's do that just for fun, because we have all this extra time on our hands with this pandemic. Okay, so I'm going to touch my red probe to the higher potential, the negative end, to the lower end, the negative end, and I'm getting readings in millivolts, like 0.9 millivolts, aka 0, which is exactly what I expect. So we're good on that end. So now let's break the circuit and measure the total current of the circuit. So remember, I moved my red probe back to this hole because this is the ammeter setting. I can measure amps with this, and these yellow, oh, I just noticed that. It's yellow colored and that's yellow colored. Okay, so now remember, to connect an ammeter to measure current in a circuit, you have to break the circuit. So to measure the total current, I'm going to first measure the very first path that electricity goes, because that's the total current before it gets split up, right? And I'll measure that. So I put my red prong on the higher potential, my black prong on the lower potential, and I get about 0.54 or 3. I'm just going to say 0.5 amps. So total I, this is so hard, equals 0.5 amps. And we know in a parallel circuit, the total current gets split into however many branches the current can flow into. Right now, we only have two options, right? Current can either go through the first bulb or the second bulb. So we have 0.5 equal to something plus something. How do we measure that something plus something? We break the circuit. Come